Welcome back to Introduction to Computer Networks at NTU. I'm Polly, your instructor. So as usual, let's check out the assignment due this Saturday. So first is the PA. So PA6 is straightforward, just like PA5, so no worries. And there are 4 more quizzes to submit this week, but very likely just 3. Okay, very likely just 3. So all those will be due Saturday, 6 p.m. And hi guys. Yeah. Okay, really nice week. Yeah, really nice weather this week. Hi. Oh, Sophia, finally, in normal English letters. Okay, great. Jeremy, Zach, Jiabao, great. Oh, and hey, today we have a bullet 4, point number 4. Yeah, so this announcement is special. Guys, pay attention. Polly will be on conference travel the week after next week. Okay, so Polly will be attending a conference 2 weeks later. That will be week 11. This is week 9. Okay, so 2 weeks from now. And she will not be able to stream the lecture live from another country from the conference because Polly is co-chairing the conference and will be very occupied. Okay, so please, okay, instead of attending the live lectures, please watch the recorded live streams from last semester, okay, spring 2023, okay, and pick up these topics next, okay, and complete the quizzes associated with these topics. Okay, Sophia, you have many YT accounts. Sure, we all do. Yeah, privacy is a major thing these days. I understand. Yeah, so hey, more specifically, which video, which part of spring 2023 live stream you want to watch for week 11? Those will be S23 episode 19, episode 20, and the first half of episode 21. So this is approximately 3 hours. Okay, so this is in place of the normal live streams we'll be having. And so after Polly returns, that will be week 12. We'll go on with the newer topics. Okay, so we'll not be reviewing these topics. And by the way, Polly would also make the quizzes for week 11 available early. So there'll be week 11 quiz something channels ready for you to complete. Okay, so these live stream recordings, you will see Polly popping up quizzes and asking the class, the spring 2023, to complete the quiz. And you will just, work on it in the meantime. Pretend that you did not see others' solution. You see that it's kind of important because you want to try if you understand what's being told. And so you can exercise. Okay, seeing the solution already, and then you try to come up with your own thing. You might be assuming things too much. There might be things that's not exactly clear to you. All right, so that's the pitfall of knowing the solution first before trying to answer the questions. But I understand, without knowing the solutions and trying to tackle the problem in the forward direction, it will be a little bit more time consuming. But I think that time is a lot of times necessary for you to really expand your intellectual capacity, your knowledge base. All right, great. So with that said, let's check out the topics today. Hey guys, wouldn't this be exciting? So we are in transport layer, and finally we'll be talking about a real protocol in the transport layer. Until now, all we talked about are concepts, okay, of RDT and how general solutions are to do RDT, reliable data transfer. Starting from today, we'll check out how TCP does reliable data transfer. Okay, so this is the first video. It's an overview, and you will see Polly quickly overviews section 3.5. Okay. Last week is all section 3.4. We talk about RDT and generations of RDTs from less efficient in utilization to more efficient in utilization, the pipelined RDT. And in this video, you will see how TCP's RDT is a little bit more general than those RDTs we've talked about in section 3.4. And those RDTs are kind of, designed or defined specifically to keep it simple. So for example, we keep the data in one direction. So data only comes from the sender to the receiver. And from the receiver back to sender, there will be just acknowledgements and nothing more. Okay, so in the overview video, you will see that this time in TCP, data can go bi-direction. And something else very different is how we count data. Previously, we do what? Hey, sender send one packet, sender send two packets. We count the data by packets. But in TCP, we started counting data by bytes. And this is very important and necessary because in reality, when we are allocating memory space for the sender window, do we allocate memory by packets? We can. We don't know what the packet size is. And besides, in a normal TCP connection, you have packets coming in different sizes. So we need to allocate memories, 4 megabytes of memory, 4 gigabytes of memory. So we need to count the data by bytes, okay, in TCP. So this overview video, 6.5 minutes. And this is 3.5, connection-oriented transport, particularly the TCP protocol. So in this particular section, we're definitely going to talk about the RDT implemented in TCP. Now, provided the background, okay, very extensively in 3.4, you should be able to understand TCP's implementation of RDT, TCP's design of RDT. Now, in addition to the RDT in TCP, we are also going to talk about the packet format of TCP. And that is what the segment structure meant here by the textbook authors. And then there are two minor functions, but necessary functions in TCP. One is called the flow control. The other is called the connection management. And this is the overview. TCP we know already. Just like UDP, it's what? End-to-end process-process communication. So end-to-end there can also be referred to as point-to-point communication. We have a sender process and a receiver process. Now, in this connection here, what we're doing is to do reliable and in-order data transmission. Now, what's a little bit unusual when we talk about TCP is this. Instead of earlier, when we were talking about the general principles of RDT, we are counting the data by what? Packets. Packet 0, packet 1, packet 2, packet 3, so on and so forth. But in TCP, we count data all right, but we count the data by the bytes. By 0, by 1, by 2, and so on and so forth. So that connection here, when we are passing data around, we are actually passing a stream of these bytes. Right? So there's no more message boundaries, or there's no more packet-to-packet separation. Right? And last, this is actually telling you ahead of time that TCP's reliable data transfer is doing this, the pipeline-based RDT, so that we have a window size there, where the size n is definitely larger than 2. And so we could have multiple packets in transit so that the utilization of the connection there can be higher. Okay. Now, what we don't know quite yet is this. This window size is also used not just for reliable data transfer. Later on in section 3.6 and 3.7, you will also hear it's also for the congestion and flow control. Okay, so there's going to be a window size for flow control. And the window size for RDT is also used, okay, for congestion control. And conveniently, in flow control, what's being done is the receiver will every now and then tell the sender, hey, you might want to slow down or you might want to speed up depending on how much the buffer space is occupied at the receiver side. You see what happened at the receiver end of the TCP is this. Data will come in continuously from the sender. Data will be extracted and passed up to the application layer process. So there's an incoming rate and there's also an outgoing rate. When the outgoing rate is slow, incoming rate is fast, then you see the buffer space is quickly exhausted. Okay, so at that point, receiver tells the sender, hey guys, slow down. All right? Now, the other way around, if the buffer space is very empty, then telling the sender, feel free to send more. So flow control there. Okay, mainly allowing the receiver to tell the sender, hey, slow down or speed up, such that there's no congestion occurring at the receiver side. Because if the incoming rate is high, outgoing rate is slow, over time, when the buffer is exhausted, the incoming packet, incoming data will be what? Will be dropped. Okay, so delay long, and you see also data loss there, right there at the receiver. So this is to avoid also congestion, but it's a bit weird. It's actually to avoid congestion at the receiver side, not quite in the middle of the internet. Okay, so when I say in the middle of the internet, I actually meant congestion in the core of the internet. Sender process, receiver process is what? At the end of the internet, at the edge of the internet. So flow control there is to try to control the end processes such that there's no packet drop at either end. Congestion control, on the other hand, is to control such that there's no packet drop or congestion in the middle, in the core of the internet. And TCP, being connection-oriented transport layer service, is sending some messages at the beginning before data can be transmitted. So there are some handshaking being done right before the data exchange. And these handshaking messages are there to set up the initial states of the sender and receiver. And that is called the connection management part of TCP. Last but not the least, there's a mindset change here in a TCP connection. Data traveling in a TCP connection is now full duplex. What I meant by that is the data flow is going, bidirectional. Okay, so two processes or point-to-points, will be sending data this way as well as this way. Now, why is this a major mindset change? If you recall in 3.4, when we were talking about these reliable data transfer mechanisms, we always say what? This is the sender side of RDT, and this is the receiver side of RDT. What we are saying there implicitly is also, this is data sender side of RDT. This is the data receiver side of the RDT. Data receiver there, receive data. It transmits something as well, but it's transmitting only what? The feedback messages, the ACMEX messages. The receiver there does not send data. So TCP here, you see, being more general, data can go either way. So the two processes will be implementing both the sender and receiver finite state machines. And the last bit is this. MSS, a special term that is referring to this, the maximum segment size. If you recall, a packet at the transport layer is called a segment. So maximum segment size is essentially the maximum packet size. Okay. In reality, in actual TCP implementation, we're still sending data packet by packet. But the sequence number, we'll be checking to do reliable data transfer is now counting the bytes of the data, not the packet numbers of the data. All right, so that's the overview. You see that already TCP's RDT is pipelined. Okay, and there are a couple other additional mechanisms to maintain the connection somehow, right? The flow control and the connection establishment mechanism. You'll hear more about each of these. Okay, now to begin, let me introduce TCP's packet format first. By the way, a packet in the transport layer is called a segment. So this next video is the segment format as well. So it's 5.5 minutes long, a little bit long, but you will see that there are some parts that are similar to UDP's header. Okay, but there will be some new fields being introduced in order to do reliable data transfer and other things. TCP segment structure, aka the packet format. It does look a bit complicated, definitely more complicated than the UDP packet. If you recall, in UDP we do have these fields: source port number, destination port number, as well as the checksum. Okay, so all these are what called the header fields. So in TCP packet, the header part is substantially larger. While the data part, it's still variable lengths that could be large, could be small. So the overall structure in TCP packet is actually very similar to UDP, two parts, header and data. The main difference is where? The header part. Okay. So some of the header fields repeat itself. We see source port number and destination port number as well as checksum also in TCP packet header. But what else in the UDP packet header that we don't have or we do have in TCP's packet header? And here's UDP's packet format. So we do see source port number, destination port number, checksum. And what else is in UDP's packet header? The length. So that is the entire packet size, including the header as well as the bytes in the segment. So data and header together, okay, in this field, the length. Do we have length in TCP's packet header? We actually don't. The thing that we have the closest is this, the header length. So the length in TCP packet header counts only the size of the TCP packet header, while the length in UDP's packet header counts the entire UDP packet. Given that we're already talking about the header length, why don't we talk about these special bits, okay, special flags in the TCP packet header? First is the A flag. Okay, so this is called the ACK flag as well. When it's turned on, when the ACK flag is on, that's indicating that the acknowledgement number here is actually valid, meaning that the sender of this packet is trying to tell the receiver that it's trying to acknowledge certain bytes being received. Okay. And these three R, S, and F bits, they are there to indicate packets being used to do connection management. So for example, SYN here, the SYN packet is to set up connections. The FIN packet, which is Latin for the end, yeah, conveniently, okay, is to tear down a connection. RST, or the R bit here, means reset, that is to re-establish the connection, to re-initialize certain parameters between the sender and receiver of a TCP. And P bit, yeah, P stands for push, that is to push data now. So this is to actually pass the data out as soon as possible, but it's generally not used. Just like the U bit, this is urgent, so this is indicating that whatever data is here is urgent. So pass it out through the network or to the application layer as soon as possible. Okay, so you see urgent, the purpose, and push, somewhat similar. The ambition of the network engineers much early on is also that hopefully a data network or the internet can also allow urgent data being sent, just like we could make it 911 call or in Taiwan 110 call to get police's attention or the fire department's attention as quick as possible. But unfortunately, the way the internet is designed is just not very good for urgent critical data transmission. And yeah, we said that these are not used, so there are a number of bits not being used. But the fact is actually there are two more bits being used. It's called the C bit and the E bit. Now these two bits are not really for reliable data transfer service, not for connection management purpose. They're actually there for congestion control. Okay, but it's not quite the congestion control implemented in TCP though. Okay, it's just that the engineers are expecting, okay, later on TCP's congestion control can be extended, okay, together with the core of the internet such that we could do better control. So there will be two more bits we'll have to talk about, but it will be at the end of chapter 3. And that takes us to, yeah, the urgent data pointer. So this is actually working with the urgent bit. When the urgent bit is on, then the transport layer of TCP is going to look into this pointer and then grab whatever the data that's here indicated by the pointer. So this data here will be extracted and passed out as quick as possible. And receive window here. Yeah, this is the window size for the flow control. Okay. If you recall earlier in the overview, yeah, we say flow control is for the receiver to tell the sender, hey, slow down or speed up. And when the slowdown is to be communicated, receive window here will be a small number. If the receiver wants the sender to speed up, the receive window there will be larger. And the last two fields in the header are these. Yeah, the sequence number as well as the acknowledgement sequence numbers. So these are exactly for the reliable data transfer purpose. But keep in mind, we're now counting the bytes, okay, not packets. All right, so substantially more fields in the packet header. Next topic, how do we do byte counting? I'm going to separate this topic into two videos. So you want to follow both the videos so you can answer quiz 23. So first is to introduce the idea. TCP sequence number and ACK numbers, these are very important fields. Let me elaborate more here. First, the sequence numbers. So what the sequence number says in the packet header is to tell you this: the byte stream number of the first byte among all the data bytes in the packet. So, but what is the byte stream number? Yeah. Let me explain. This is the original message, which can be really large, generated by the application layer process. Now, as it's pretty long, right, each byte can be indicated in sequence in byte stream number. So this is byte 0, byte 1, byte 2, byte 3, byte 4, and so on and so forth. So these numbers, these serial numbers, are the byte stream numbers. So when such a message arrives at the transport layer, the TCP sender is going to what? Break them down into smaller parts. Let's assume that in the first segment, it contains only 3 bytes of the data. So in the header here, the sequence number is going to be what? Oh, the byte stream number of the first byte of data, which is 0. For the second packet, in the header sequence number field, what should be the value? It should be the byte stream order of the first byte of all the data, right? So 3 here. Okay, so that's what sequence number meant. And it tells you where the first byte of this data packet is in the original message. So we could track whether all the bytes in the original messages are being transmitted successfully. Second, the acknowledgement number. Now to explain this, let me tell you, TCP implements, just like go back in, cumulative acts. So that number there, based on your knowledge of go back in, should indicate what? The last byte of all the data received correctly at the receiver and in sequence. But, well, it's actually not quite. So TCP's acknowledgement number is actually counting 1 byte further. So it's the next byte the receiver is expecting. So that number is the number of the next byte the receiver is expecting. Therefore, it will also be the what? The sequence number of the next data packet coming from the sender. And with that said, many of you will probably guess that TCP's reliable data transfer mechanism is similar to go back in. You are actually correct. So let me borrow the diagram that I've been using to explain the sender side behavior of go back in here. The only difference is just that previously, now each rectangle indicates a packet, but now we are counting bytes instead of packets. So each of these are what? Bytes. So we have green bytes, yellow bytes, blue bytes, and gray bytes. But similarly to go back in, the green bytes are what? The bytes that are already sent and acknowledged. Yellow ones are the bytes sent and not yet acknowledged. Blue bytes are those usable, so if there are more data the application layer process wants to send, we could now turn these blue ones to yellow. So usable but not used. Gray ones, not usable because it's what? Outside of the window size, outside of the window limit. Now, the sender generates a data packet. What's going to be in the sequence number is what? The first byte of the data and the byte stream number of it. And if an acknowledgement is coming back to the sender, acknowledging this packet, the acknowledgement number here is going to indicate what? The byte stream order of the next yellow packet. So this first one here is going to turn green. Yeah, so ACK number here is the first yellow next. And the last bit here is again about TCP's RDT being very similar to go back in. So if you recall, go back in's receiver, when it receives out of order packets, what does it do? It drops all the out of order packets. Now that is actually a wasteful use of network bandwidth, isn't it? So TCP here allows a bit more flexibility. The programmers themselves can decide whether to buffer the out of order packets or to drop them. Yeah, so by now you can see TCP's reliable data transfer is pretty much go back in, but less wasteful go back in. And let's check out an example before we work on quiz 23. Now let's exercise what we learned about the TCP sequence numbers and ACK numbers using a simple telnet scenario. The setting is this. We are here at host A. We've already started the terminal and it's connected to the remote machine, host B. So what happened in the telnet is this. When we hit C, a key locally, okay, so user type C, what happened is this. Host A sends a byte, that character C, to the remote machine. Now the remote machine is going to receive this and see what to do with it. Okay. Now because it's a very straightforward character C, not like escape or control C, therefore what it does is going to be simply echo back the character C to the local host. So host A here will receive the echo C and then display on the local terminal. Okay. So once again, host A here has 1 byte to send. Host B here has 1 byte to send. And that's the scenario. Now, the 1 byte of data generated by the telnet process. As soon as it arrives at the transport layer, we're going to add header to it. So sequence number, ACK number being added to it. And the data is simply a character C. Now, when this packet arrives at host B is going to what? Yeah, echo with the same character C. And in the meantime, acknowledge receipt of the data packet earlier. Right? So what will be the sequence number and ACK number we'll be generating? Well, we send 1 byte of data. What should be the sequence number there? Well, go back here. The ACK number is indicating what is the next sequence number the sender of the ACK packet is expecting. Therefore, sequence number we know should be 79. Now, what should be the ACK number here? Well, ACK number is what? The last byte received and then counting further by 1 byte. What is the last byte received? Yes, 42, because there's only 1 byte. And counting further, we say ep15, and this is also host B telling host A what is the next data byte expected. And therefore we see the next packet coming back from host A, sequence number 42. But host A here is not echoing C anymore. All it needs to do is to what? Acknowledge receiving this packet. Right? So ACK packet needs to be what? Last byte received by host A, which is 79 because there's only 1 byte. And counting further by 1. Therefore, we get 80. So you see, quite obviously, in order to find out what is the next sequence number, look at the packet coming the other direction's ACK number. In order to find out what is the ACK number, look at the packet sequence number coming the other direction. Similarly, sequence number here, look at the ACK. The ACK number, look at the sequence of the last packet coming the other direction. All right, so you are now well prepared to work on quiz 23. All right, so guys, let's look at the scenario on the left first. Okay, so this is the simpler case where we still assume data going one direction and it's coming from host A to host B. So this is the packet being sent, starting with byte 100, and this packet carries 8 bytes of data. And so in return, host B here needs to send back an acknowledgement. And that acknowledgement should be the next byte host B will be expecting. So the starting byte is 100, and there are 8 bytes. The last byte will be 107th. And therefore, the next one host B is expecting is 108th. All right. So similarly, the sequence number, what we need to do is to check the ACK previously. Okay, and it's 108. And this time, data is 12 bytes. The ACK is to check the sequence number. And 108 carrying 12 bytes of data, therefore, okay, in return, the ACK should be 120 bytes. All right, so that is the simple case. Now let's consider the complex case or the bidirectional case where data go both ways. So host A here sends the data, sequence number 20, size 8 bytes to host B. in the meantime, it sends also acknowledgement to host B's data earlier. Okay, good. So B now receiving this packet will need to respond with an ACK, right? So this is associated with the data. And host B here might have data to send, which will start from byte A. And if the data size is 49 together, the two of them will also decide the next ACK from host A. So you see that two directions of data ACK and data ACK and data ACK are going on at the same time. Okay, so data go with this ACK, and this ACK maps to this data, and again. Okay, so this is one direction, and then of course there's the other direction. Good. So quiz 23 here asks you, to tell the value of A, B, C, D, E, F. All right, great. Now let's move to Discord. Channel W9, quiz 23. Aha. Very interesting. Guys? Yeah, very interesting. Okay, you guys are too fast. I guess you see the questions, right, while Polly is explaining, and you get the answer. So let's see. Guys, the rest of you, try to catch up. Let's see if Team 1 gets it right. So let's see. A is what? Sequence number of the second packet coming from the host. And you look up the ACK number. Yeah, A is 100. You're correct. Is B correct? B should be what? The next packet expected. 20 is the first byte sequence and size is 8. No, I don't think B is 21. Okay, let's see Team 5, if Team 5 gets this right. 28, yeah, because the first byte is 20. A bytes in the packet. Therefore, the ACK should be 28, right? And if B is 28, yeah, C is 28. Let's see. C is 28. Great. Team 5, you got it. And D, let's see. What is D? D is the ACK. So you look at A and 49. And we know A is 100, so 149. There you go. And D, once again, decide what E should be. E, therefore, is also 149. And F is determined by the previous packets, C and the packet size. And we know C is 28, and the packet size is 12 together. Oh, sorry. 12. So together is 40. Good. So Team 5 here is the first one to get everything right. Great. Team 1, hey, great work. Okay, just off by a little bit. Okay. By the way, Zach, this is not exactly a telnet connection as we illustrated in the example. Okay, so in quiz 23, not a telnet connection, that echoing just one byte. Okay, Team 3, no, not quite right, but hey, Team 4 is right. Team 12 is also right. All right. Okay. Miguel, yeah, you guys want to think about it again? Yeah, think about it again. Let's see. Yeah. The rest of you, get the answers right. Very good. So hey, I guess it's relatively easy. It looks complicated, but if you sit down and think it through, it's not that complicated. All right. And now we move on to the next topic. To talk about TCP's reliable data transfer mechanism, we need to talk about this thing. If you recall, right, in the RDTs, in section 3.4, to handle the case of having packet loss, the sender will need to wait some time until the timer expires, then retransmit. So there's this timeout interval, okay, the retransmission timeout interval. Previously, we never talked about how we set that timeout interval. But TCP being a real protocol that's implemented and that needs to function, we need to give it a specific value. Okay. So the next videos, there are 2 of them, is to talk about how TCP estimates the timeout interval. And the first part talks about how TCP estimates first the round trip time, which is a very important base of the timeout interval estimation. This video, 4.5 minutes. Now, with the fundamentals of TCP packet format, TCP being bidirectional, and we're actually counting bytes instead of packets. So with these out of the way, we can now come back to talk about the reliable data transfer mechanism implemented in TCP. Before Polly shows you the finite state machine of TCP's RDT, let's define this thing first. It's called the timeout interval or timeout value. Now, TCP being implementing a reliable data transfer protocol, it needs to also define this thing clearly. What is that? If you recall back and go back in, we said that after packet gets transmitted, we start a timer. That timer is going to tick, tick, tick. If an ACK does not come back before that timer expires or that timer times out, then what? We retransmit packet. So this timer there is to allow us to decide whether a packet is lost inside the network. So it's part of the RDT mechanism that is very critical. And that interval determines how long the retransmission is going to go. And that influences the performance of the reliable data transfer. We know already in some earlier example, if that timer is set too short, so packet can sometimes travel the internet a bit longer than usual. If that timer is too short and expires, then retransmission right before ACK arrives back, then this retransmission there is unnecessary and premature. Okay? That is not a good thing in terms of bandwidth consumption. So, not good. If that timer is too long, the intuition also says it's going to take a long time for the sender to discover there's a packet loss and try to recover from it. So you see that the user experience with sending data over this connection is not going to be good. Okay, so slow reaction to packet losses. Either case, not good. So how do we find a balance? How do we set or how do we estimate the timeout interval? You see, it's not that far-fetched. You heard Polly saying this already. The interval should at least cover what? The time data travel to the receiver and the ACK coming back from the receiver. And we know this is called what? The round trip time. But you also heard Polly saying that sometimes it takes longer for the data or ACK packet to travel the internet. Therefore, the timeout interval there should be set to cover longer than most of the round trip time that the pair of sender-receiver might experience. And that is the idea behind how TCP estimates the timeout interval. And you see also, in TCP, it needs to observe the round trip time repeatedly in between the pair of sender and receiver. Right? And this is exactly how it's done. Okay. For a pair of data goes out and the ACK come back, it calculates the time differences between receiving of ACK to the sending of data, and we get a sample RTT. Now, there will be a lot of these sample RTT for each data and ACK pair, but we will ignore the data ACK pairs due to retransmission. So some of these data might get lost and therefore they get retransmitted. When we receive an ACK for such a data, it could be a bit confusing, right? What is the right data sending time to subtract in order to be sure that this is really estimating just the round trip time and not covering a premature timeout, things like that. And we get lots of these sample RTTs, and they could vary quite a bit. So you see that it's actually not good to use the sample RTT as the timeout interval for the next packet. Not good. So what TCP does next is this, to get a smoother estimation of the round trip time. Okay? And that is done by taking the average of multiple recent sample RTTs. All right, so estimating the round trip delay, get a pair of data and the corresponding egg and calculate the time difference. Now, but you see, internet, right? Traffic goes on and off. So the round trip time, okay, one can observe over a connection can vary as well. Okay, even if you calculate the average, right? Chances high that you very often will need to retransmit packets unnecessarily, and that is not good. So to address this variation, you will see in the next video that on top of this round trip time, estimated average round trip time, we add something extra, okay? Add a buffer to it so that the chance of doing unnecessary retransmission is minimized, okay? And this video will be long, almost 7 minutes. So what Polly brings up here is essentially the line of code in TCP's implementation, estimating the smoothed RTT. So the estimated RTT, this variable is to refer to the smoothed RTT. Now the smoothed RTT next is going to be the smoothed RTT now, and take a weighted sum of that to the current sample of RTT. Okay, so current smoothed RTT, and take the weighted sum of that to the current sample RTT. Okay, so we're taking the history into consideration, that's why it's called the moving average, and we're using a special factor alpha here, so it's a weighted moving average as well. Now the reason that it's called exponential is because of this, right? So the whole thing is the current, okay, smoothed RTT. Now this whole thing is going to be used as what? The first term of the next estimation. So you see, okay, the current smooth RTT is going to be weighted what? 1 minus alpha, actually, 2 times. So the current estimated RTT 2 rounds later will weight exponentially less. Okay, 3 times 3 exponents less, 4, and so on and so forth. So the past sample, the influence of it will decrease exponentially fast. Oh, and by the way, alpha is only 0.125. That is because, yeah, we don't want to weight too much on the instantaneous RTT because otherwise it will be what? Also fluctuating, okay, not exactly smooth. And here shows, yeah, the instantaneous RTT and the estimated RTT, the smoothed estimation, how they look like relatively. And this is actually actual measurement between UMass and OIRCOM again. So the blue one that fluctuates more, yeah, like these. Yeah, these are the instantaneous RTT, the sample RTT. The pink one then is the estimated RTT, the smoothed, the average RTT over time. So you see that although the blue one fluctuates a lot, but the pink one, yeah, relatively smooth. And you see also, yeah, generally as time goes along, the round trip time tends to be longer. And so you see the pink here, yeah, the smoothed average RTT is tracking the increase of the RTT relatively well. But be careful here. The estimated RTT is definitely not quite yet the timeout interval used by the TCP. Because if you do, you see these guys here, yeah, the round trip time is actually way longer than the timeout interval. So for all these guys, you will get premature timeouts. So the estimated RTT there is certainly not covering most of the round trip time observations. So there's more. Therefore, in TCP, the timeout interval is the estimated RTT plus a safety margin. So estimated RTT is the what? The average. And the timeout interval should be the average plus a safety margin there, such that all these simple RTT fluctuates in the middle will be covered. Or, yeah, the more simple RTT being covered by the safety margin, the better. Challenge next is to set the safety margin. And the thinking behind setting the safety margin is this. If the sample RTT fluctuates a lot, yeah, we use a larger safety margin, right? Small fluctuation, smaller margin. Therefore, the key is to estimate the variation of the sample RTT. So the challenge boils down to estimate the variation of sample RTT. And that can be done this way. So sample RTT is the instantaneous RTT. And estimated RTT there is the variable storing the average RTT. So the deviation is essentially what? Yeah, the sample RTT subtracting the average RTT. Right? Now, of course, we will not be using this, by itself to set the safety margin, because this is also what the instantaneous deviation, right? So let's estimate the smoothed deviation of round trip time, okay, by the EV-RTT, and borrowing again the technique, the exponential weighted moving average, to get the smoothed depth RTT. So the next depth RTT will be the current depth RTT and the weighted sum of that to the instantaneous deviation of RTT. Alright, so the only thing left is just the beta factor, and it's also set to a small value so that we weigh less on the instantaneous deviation. As to why it's 0.25, not 0.2, not 0.125, these alpha beta values are usually given because people have been using these values and they seem to work out fine, and engineers later on will just borrow using the same setting. And now finally, the timeout interval. It is the estimated round-trip time plus the safety margin, which is determined by the deviation of round-trip time. Now, as to why 4 times the deviation of round-trip time, the original designers of TCP, they don't usually talk about this. I mean, the 4 could be a result of repeated experiments, but Poly guessed also it could be because of this. They have assumed the sample RTT distribution being normal. If you recall back in Statistics 101, right, normal distribution is for a sample such that if you plot the histogram of that sample, you see a bell shape. The average is usually in the middle where there are lots of samples, and the 2 ends, few samples. In normal distribution, starting from the average, if you add 2 standard deviation, subtract 2 standard deviation, it should cover what? 95% of the value range of all these samples. So by adding 4 standard deviation here, timeout interval here is covering more than 99.99 something% of these sample RTTs. That is also saying, setting the timeout interval this way, there's going to be very, very, very few premature timeout in TCP.
Nice, isn't it? When so TCP estimates also the variations of the round-trip time estimation, right? The higher the variation, the larger the buffer. So that's the idea. Okay, but you can see that there are also some ad hoc choices. 4 times the deviation, adding to the average round-trip time, for example. And on the internet, a lot of times, or for general engineering problems, a lot of times we kind of choose these parameters, okay, by experience. So we call them the empirical choices, empirical design, okay. And you know what? It is all the time we have. The next video is going to be about the RDT, the actual RDT implemented in TCP. And I'll be introducing finite state machines again, but this time is the exact one used by TCP. And we'll start that tomorrow. By the way, tomorrow's lecture, we'll start with some heavy stuff because TCP not only do the go back and pipeline RDT, there are some additional improvements, as you can see on the outline slide here. There's something called delay AG. There's also something called fast retransmission. So there are a couple more tricks, okay, people implementing to TCP to speed things up or to reduce some control traffics. And tomorrow, a little bit later, there's going to be, we're going to start another topic called congestion control. Okay, so 2 more quizzes coming up for sure tomorrow. And with that said, I say goodbye. I see you tomorrow. Okay, bye. Jeremy is the first one to say bye. Jeremy, you're paying attention to the lectures. That's great. Okay, bye. See ya.